Okay, note down the problem. Yesterday we have discussed about one problem. Okay, and we found that critical speed resistance and critical speed. So today we'll solve one more problem. Just all of you note down this problem. So have you finished this writing the problem?
Yes, sir.
So shall we start now? So here the magnetization characteristics of a shunt generator running at 800 RPM is as follows. So as given the field current and the no load voltage is given. Okay, with the help of this, we need to find out the critical resistance of the shunt field circuit. And if the field resistance circuit is changed to 75 ohms, then what will be the critical speed for the machine to build up the voltage? Okay, so we need to find out the critical field resistance. Okay, and critical speed, right? So RCR, critical field resistance, we need to find out, and then the critical speed with the help of graph. Okay, so I will take up a graph sheet, and then with the help of this table, I will draw the characteristics. Okay, just you take your graph sheet and then take the values. Okay, so here I will consider 0, this is 0, and now this one is 0.5 amperes. Okay, 1 ampere. So on the x-axis, I'm taking the field current. Okay, and now I will assume that the scale is the scale x-axis 1 unit is equal to 0.5 amperes, and y-axis 1 unit is equal to 30 volts. Okay, so this is the scale what I assume. So here this is a 30 volts. So your field current will be 0.5, 1.5, 2, 2.5, 3, 3.5, 4, 4.5, and 5. Okay, and this is 30, 60, 90, 120, 150, 180, 210, 240, 270, and 300. So this is a scale into the y-axis. So the y-axis is represented with the nodal voltage EA in volts. Okay, is it clear? Do you have any doubt? Is my voice is clear?
Yes, sir.
Yes, sir.
Okay. Screen is also clear, no?
Yes, sir.
Yes, sir.
Okay, then. So next what we have to do is just I will take the values. Okay, then I will draw the graph. So for the first one, the field current is 0. Field current is 0. Your induced voltage is 10 volts. So each unit, the small units are 6 volts. So 6 plus 4, 10. So I will put up 1 point here for the field current of 0 amperes. And then next one for the field current of 0.5, your voltage is 50 volts, and therefore 30, 36, 42, 48. Okay, 52. So here I will put up this point. This is for 0.5 and the voltage is 50. Okay, and next one 1 amperes. For 1 amperes it is going to be 100. So this is a 90, 96. So I will take a point here. The next one for 2 amperes. So here for 2 amperes the voltage is 175. So 153, 165 plus 10. Okay, 174. So 174 plus 6, 180. So this is going to be here at this point. Okay, so this is the point where we need to put. Okay, next for 3 amperes the voltage is going to be 220 volts. So this is a 3 amperes here. This is 210 volts at this point. point, this is 210 volts, 210 plus 260. Here for 4 amps, it is going to be 245. So here, this is going to be here. And then for 5, it is going to be, for 5, it is going to be 262. So 240, 255 plus 6, 261. Six, 58, 58 to 64. So here, this is the point. Okay, so these are the points. Is it clear? It points any correct na? Ikkada mistake jarigindha chudandi. Is these points are correct?
Yes, sir.
So next what I'll do is just I will join these points. So you can observe that this is a linear portion. Now the saturation is reached. This will be like this. Okay. మీరు గ్రాఫ్లో కొంచెం నీట్గా డ్రా చేయండి. This is a straight line. This is a graph. Okay. So this is nothing but the open circuit characteristics. 800 RPM. Okay. So this one is the open circuit characteristics. So have you all of you finished this?
Yes, sir.
Yes, sir.
ఇది డ్రా చేసిన తర్వాత next what we have to do is just we have to draw a tangent. I will take with another color here. So we need to draw the tangent. So I will start from this point. So tangent is nothing but it is touching the maximum points on the linear portion of your magnetization characteristics, and this will be like this. This is your tangent. This is a tangent to the initial portion of open circuit characteristics. Okay. Is it clear?
Yes, sir.
Advaina? Then next. So we'll take 2 points to find the critical field resistance, because the slope of this tangent will give you your critical field resistance. Am I right? the slope of, write that, the slope of the tangent to open circuit characteristics will give the critical field resistance RCR. The slope of the curve will give us the critical field resistance. So I will take the 2 points here. So at 210 I will consider this. మీరు గ్రాఫ్ డ్రా చేస్తే వేరే పాయింట్స్ వస్తాయి. ఓకే, మీరేం టెన్షన్ పడాల్సిన అవసరం లేదు. నా దగ్గర రఫ్గా డ్రా చేస్తున్నా కాబట్టి just I will get the rough values, but you will get the exact values because you are drawing it from the graph. Okay, so this is a point A and this is a point B. Okay, so at this point I am taking, and this is a point. So here this point here, this is nothing but, here this is a point P, and here I am taking, so this is the point, okay, this is a point Q I will assume. So it is 2.5, so 2.1, 2.2, 2.3, 2.4, 2.5. Okay, so your critical field resistance RCR is equal to, the voltage. Okay, R is nothing but voltage AB divided by the current. This is the field current PQ. So this will be equal to, so B point is 240, so B is 240 and the A is 210. So 240 divided by 210 divided by 2.4 minus 2.1, because these are the points are 2.1 and this is the point of 2.4 amperes. Okay, so this will be equal to 240 minus 210, so this is a 30 divided by 0.3, so this is around 10, so 100 ohms. Okay, so this is around 100 ohms. So critical field resistance is 100 ohms. So మీరు చేస్తే 110, 120 అలా వస్తుంది. Just don't bother about that. ఓకే, మీరు ఎగ్జాక్ట్గా స్కేల్తో డ్రా చేస్తారు కాబట్టి ఎగ్జాక్ట్ స్లోప్ వస్తుంది. సో నేను రఫ్గా డ్రా చేశాను కాబట్టి జస్ట్ ది స్లోప్ విల్ బి వేరీస్. యాక్చువల్ ఆన్సర్ ఇస్ 108 ohms. From the textbook I have taken this. This is going to be 108 ohms. So మీకు నియర్ బై అటు ఇటు వచ్చినా కూడా ఆన్సర్ కరెక్టే. ఓకేనా? Is it clear here? This is the first point to find the critical field resistance. Okay. Yes, anyone? Srinivas?
Yeah, okay, sir.
Okay, so అందరు ఫినిష్ చేశారా? అది
1 minute.
Yes, sir.
ఫినిష్ చేశారా? The next one will solve the second one. Okay, so this is the first part of our problem, finding the critical field resistance. Then the second part is what we need to find. What is the second part from our problem?
Critical field
So here,
resistance.
if the field circuit resistance is changed to 75 ohms, the field circuit resistance is changed to 75 ohms, what will be the critical speed for the machine to build up? So here he has given that field circuit resistance is 75 ohms. So we need to consider this. Okay, so just you take that. Then for the RF line, okay, so here I will consider the second part. Okay, so for the field resistance, is equal to 75 ohms. We need to find the critical field Okay, critical speed we need to find out. So to find out that, we need to draw the RF line. Okay, so now we have to draw the now draw RF line. RF line. So how to draw the RF line? So to draw the RF line, I will consider that voltage E naught or EA. This is equal to RF into IF. RF into IF, and therefore this will be equal to RF is given at 75 into, just to take up any current here. So we need a pointer. Okay, we need a point here, and therefore I will consider this 3 amperes. The field current is 3 amperes. So this will be equal to, so 75 into 3, this will be equal to what? 225 volts. Okay, so EA is 225 volts. So the point, we need to locate this point, 3 comma, the point 3 comma 225. So this point should be located on the graph sheet. Okay, so this point 3 comma 225 should be located on this point. So here this is a 210. Okay, 210, and this is a point 1, 2, so 12. So you're going to get a point here, anywhere here, this line. So I will join this. So this is the point with the origin. So as this is the RF line is a straight line passing through the origin. So you have to draw the line which is passing through the origin and crossing this point. And crossing this point. This is a point OB. So the line, you'll get the line OP. So this is nothing but RF line. The line OP is nothing but the RF line. So it is touch, or it is crossing your open circuit characteristics at this point. Okay. So is it clear how to draw this line? అర్థమైందా మళ్ళీ ఒకసారి చెప్పాలా?
Ma'am, explain one.
So to draw this RF line, first of all, he has given that RF, the field resistance RF is given to you. RF is equal to 75 ohms. Okay. So for this, we need to find the slope. Okay. So we need to take up the voltage. We know that EA is equal to RF into IF. So RF, we are considering it as a 75. Then you can choose any point. So you can also choose 2. Okay. So if you choose 2 into 75, so you are going to get 150. Okay. So 2, 150. So at this point you'll get normally. Okay. So 150. Okay. Just I will take up this point just like this. Okay. So for a field current of 2 amps, 75 into 2, so it is going to be 150. So this is the point. Okay. So for 1.5, anyone, can you tell me what is the 1 దగ్గర ఎంత వస్తుంది? 75 వస్తుంది అంతేనా? If you consider IF is equal to 1, so your EA is equal to 75 into 1, 75. So for 1, you need to take up this point. So 30 covered at the exactly at the middle. Exactly at the middle, you'll get this point. So for 0.5, so 75 by 2, so 37.5, so 36, so 37.5, like this. So these are the points. Okay, so you join these points, you'll get the voltage. Okay, so 75 into 2.5, so 75 into 2, 150, 150, 130, 188 something. So okay, so you'll get here. For 2.5, you'll get here. So in this way, you have to get the points, then you join all these points. So this is a straight line actually. Okay, so this is a straight line passing through the origin. Join all these points. Okay, so you will get this point. So this is nothing but RF line. Okay, so this is RF line for 75 ohms. This is RF line for 75 ohms. Okay, then next we need to find out NCR, the critical speed for the given machine. Okay, so for that what we'll do, just we'll take up any 2 points on this RF line and also on the tangent to the OCC. So this is a point. Shit. Okay, so I will consider the point here. So anywhere you can choose a point. So I will choose a point on this one. So this is a point, let us assume. Okay, so this point I will consider this as a y. Okay, and this point I will consider it as t, and this point will consider it as s. Okay, so the starting point here, this is t. So we need to take up the point on the RF line, and also we need to take the point on tangent. So as per our formula, NCR is equal to, these are the voltages. Okay, so the voltage NCR is equal to the voltage YT divided by the voltage YS. Am I right? So this is the voltage YT divided by the voltage YS into your speed, rated speed. So this will be equal to, so how much is the value here? This is YT is equal to 150. Y2 value is 150 divided by YS. So YS is 1, 2, 3. Okay, so 18. So each unit, the small unit is 6 volts, and therefore this is covering 3 points here. This you can observe. This is a 3 points. So 3 times of 6, this is 18. 18 plus 180 is 198. So 150 divided by 198 into our speed is 800 RPM. So this will give you your critical speed. So anyone, can you tell me this answer?
606.6.
Not 6. ఓకే, మీకు నార్మల్గా 580 590 అలా వస్తుంది చూడండి, బికాస్ దిస్ స్లోప్ ఇస్ నాట్ ఎగ్జాక్ట్ స్లోప్ ఫర్ మీ. ఓకే, సో దిస్ ఇస్ 606 పాయింట్, ఎంత వస్తుంది? సో జస్ట్ యోజం, దిస్ ఇస్ 606 RPM. ఓకే, మీరు నార్మల్గా చేస్తే ఎగ్జాక్ట్ గ్రాఫ్ డ్రా చేస్తారు కాబట్టి యూ విల్ గెట్ ఇట్ యాజ్ ఏ అరౌండ్ 580 and 590 RPM. ఓకేనా? So this is a way of procedure for finding the critical field resistance and the critical speed from the open circuit characteristics of a DC generator. Okay. So now shall I close here for this problem? Then we'll go to the characteristics.
Okay, sir.
Okay. Have you finished? All of you have finished this problem?
Yes, sir.
Yes. సో మీరు ఇంకా కొన్ని ప్రాబ్లమ్స్ చేయండి వీటిపైన ఎగ్జామ్లో కంపల్సరీ ప్రాబ్లం వస్తుంది ఓకేనా definitely you'll get a question on this voltage buildup, failure to voltage buildup, and also the problem on this to find the critical speed and critical field resistances. Okay?
Okay.
Then next, we'll consider the characteristics of series generators. Okay, so the no load characteristics again. So anyone, can you tell me how to draw the no load characteristics? So this is a circuit diagram. So normally the no load characteristics is drawn between your
EG,
no load voltage versus
EG,
EG or EF.
IF.
IF, keeping the speed constant, and your IA will be equal to 0 because this is operating under no load condition. And the series generators also. So under no load condition, because the series generators, the field winding will be connected in series here. It will be like this. Am I right? Normally, the series field winding is connected in series with the armature winding. As these generators are operating under no load condition, so this series field winding carries the no load current. IA will be equal to 0. And therefore, there is no buildup of the voltage. So in this case also, so to build up the voltage, so it will be run as a separately excited generator. So the field winding is separately excited. Okay, and this field winding is carries the field current, so the voltage buildup takes place. So this voltage buildup will be same as like this. So this is also similar to the what we discussed for the separately excited generators and also for the shunt excited generators. So the characteristics looks like the same as previous ones. Okay. So I'm not going in detail. Just if you want to note down the readings, same analysis, just you take a snapshot of this, then you draw the waves. Okay, the next one, the load characteristics. So how to draw the load characteristics? So the load characteristics is drawn between VT
VT
versus
versus IF.
IF. Okay, keeping armature current and speed constant. Am I right? VT versus IF, and IS and IN are kept constant. So in this also, this will be run as a separately excited. Okay, and now the load will be closed. Okay, so once it builds up the voltage, now initially the field winding will be run as a separately excited machine. Once the voltage buildup takes place, now it will be connected and the switch is closed. Now you can take the characteristics. So this characteristics is also similar to the what we discussed for shunt and separately excited generators. So I'm not going in detail about this now. Okay, next, the external characteristics. So this is very, very important. So here, this is the main circuit for the external characteristics of a series generator. So here, this external characteristics is drawn between your terminal voltage versus IA or IL, keeping IF. IF is nothing but the shunt field, because for a series generator, IA is equal to ISC, because ISC is the current. So I will consider this as ISC, but field current should not be kept constant here, because this is connected in series with the armature circuit, so you cannot keep this as a constant. So this is also varies. Okay, and your speed must be kept constant. Speed should be kept constant. Okay. Now this is the circuit. Now practical circuit can be observed here. This is the experimental setup what we follow for conducting the series generators load test. Okay, so the first circuit, this one is the DC motor. So this configuration is nothing but the DC motor. So this DC motor, shunt motor, is coupled to the DC series generator. Okay, so this is a DC series generator, and the series field winding is connected in series with the load. Okay, so under no load condition, your current will be zero through the series field winding, and this voltmeter reads a small voltage which is known as the residual voltage. Okay, and then now with the help of this 3-point starter, your motor is started, and now as the motor is started, your generator is also starts rotating, and because of this some voltage will be built up, and that is nothing but the residual voltage. You can see that in your voltmeter. And as the switches are open, the loads are open condition, so the current through this series field winding will be zero. So the voltage buildup is also very less. And our terminal voltage equation Vt will be equal to Ea minus Ia into Ra plus RSE, and also you can consider this as a load resistance, because this resistance consisting of this load as well as the resistance of your series field winding and the resistance of your armature winding. Okay, so if this resistance, this total resistance, okay, this total resistance is less than, okay, so RT, the total resistance RT less than RCR, so similar to a critical field resistance, then only the voltage buildup takes place. So we need to see that if there is no buildup in the voltmeter, you can observe it. Okay, this may be because of your total resistance of the circuit is greater than critical field resistance, then there is no buildup of the voltage. So we need to see that the total resistance offered by the armature resistance, series field winding resistance, and compound resistance should be less than your critical field resistance. Then the voltage buildup takes place. Okay, so the voltage buildup takes place if RT is less than RCR. Then at the no load condition, your generated voltage is very small. So as the load current Ia increases, your Ea increases. In previous case, we adjusted terminal voltage to the rated voltage. Okay, then only we are applying the loads. But this is not the case with the series generators, because as the load current is very less, so the current through the field winding is less, and therefore the voltage buildup will be 5 నిమిషాలు ఒక 10 నిమిషాలు. Okay, so with the current increases, your field is also increases. Okay, so as Ia increases, your flux increases, because it is having only a series field winding, so the flux increases. So because of this, your generated voltage increases. So as the generated voltage increases, your terminal voltage is also increases. Okay, so in previous case, it was your no load voltage was kept at constant, your terminal voltage is going on decreasing. But this is not the case with our series generators, because your no load flux is less, so the no load voltage is very less. So as the load current increases, the flux produced will be increases, and your generated voltage increases, and because of this, your terminal voltage gets increased. So that you can observe a characteristics like this. So this is the characteristics, external characteristics of a series generators. Okay, just a minute. I will be back in 1 minute only. Just you draw the graph sheet. Okay, draw the characteristics. Okay. Just you all of you draw the characteristics. So this characteristics, first characteristics is a no load characteristic, and the characteristics number 2, this is a external characteristics. This is drawn between your terminal voltage versus IL. If you add up the armature resistance drop, so this is a IA into RA plus RSC, you are going to get the internal characteristics. So this resistance, this drop is due to your armature reaction. Is it clear? This first one is the no load characteristics, what we observe by separately exciting our field winding. So you'll get these characteristics. And because of your terminal voltage equation, Vt is equal to Ea minus Ia into Ra plus Rac. You can also add the load resistance, but normally we consider this two. Okay, so because of this, your Ia is goes on increasing. So at the initial stage, Ia will be very less. So your Ea is also less. Ea will be less. Under no load condition, Ia is 0. So Vt is equal to Ea. So your point will be starting at this point. Then as Ia is increases, your generated voltage Ea is also increases. And therefore, your terminal voltage goes on increasing in this fashion. So this will be varies linearly, because as your Ea is varies linearly, and therefore your terminal voltage is also varies linearly. And then after that, your flux has been reached the saturation, and therefore the development of the voltage Ea is very less, and you may get a saturated point here. Okay. So this is your external characteristics. So for this external characteristics, if you add this resistance drop, okay, so this resistance drop Ia into Ra plus Rac, if you add up this, then you are going to get the internal characteristics of the machine. Okay, so here AB, in this AB is nothing but here this one, AB is the terminal voltage. AB is known as the terminal voltage, and OA is the field current to produce this terminal voltage. OA is the this one. This is the OA is the field current to produce the terminal voltage. And then B and D, this is the resistance drop, IA into Ra plus Rac drop in the machine. Okay, and then CD. CD is due to armature reaction. CD is the voltage drop, voltage a drop due to armature reaction. Due to armature reaction. Okay, so these are the characteristics. Normally, you can observe that this voltage is gradually increasing. Okay, so this is normally used in case of boosters, where you need to increase the voltage. Okay, so this is about the external characteristics of series generators. Is it clear? Any doubt? Is it clear, everyone?
Yes, sir. Clear.
No.
Yes, sir.
Next. I will go through the external characteristics. Again, I'm not going through the no load and the load characteristics. So these no load and load characteristics are similar to the characteristics what we have discussed for all other generators. So here, external characteristics are again drawn with a terminal voltage versus IL, keeping IF constant. The field winding and the speed are both constant. Okay, so here you are having the two fluxes. So this is the flux produced by series field winding. I will consider it as a phi SE, and the flux produced by the shunt field winding is phi SH. So the characteristics of these two machines will be depends on this. Okay, so depends on these characteristics. So the net flux phi T is equal to phi SH plus phi SE. So this is the total addition. So this type of machines we are calling it as a cumulatively compound generators or cumulative compound generators. Okay, so the net flux is added here. Okay, because of these two fluxes, the net flux will be gets increased, and therefore your generated voltage increases, and the terminal voltage is also increases. The terminal voltage is also increases, and for the another case, this is a phi SH minus phi SE. This is for differentially compound generators. So differential compound generators, and therefore the net flux is gets reduced. So your terminal voltage is goes on increasing. The terminal voltage net decreases. Okay, so this is the experimental setup for conducting the load characteristics or external characteristics of a compound generators. Okay, so here this compound generator, this is a compound generator. It is having a series field winding and shunt field winding. Okay, so this is the generators, and this is again the DC motor coupled to the compound generator. This is a laboratory experimental setup for conducting the external characteristics. Okay, so with the initially this will be kept to maximum. This RFG will be kept as a maximum value, and this RFM is kept in a minimum position. Now we close the switch, DPSC switch, and you start the motor with the help of a 3-point starter, so that the field flux will be built up in the motor and it is taking the armature current. Now it starts rotating, and therefore your armature of a generator is also starts rotating. So adjust the field regulator to the rated value to get the rated speed. We need to adjust this field rheostat to get the rated speed, and therefore your generator is running at the rated speed. Then you adjust the field current. So this field excitation is adjusted. This field excitation is adjusted to the rated voltage to get the rated voltage on no load condition, because this is under open circuit. The load is not connected here, and therefore we need to adjust the field excitation to get the rated voltage. Okay, and that will be measured by this voltmeter, and it indicates that your load current IL and your terminal voltage VT. So as the load current is 0 and we are adjusting the field excitation to get the rated voltage, so this terminal voltage is reading the voltage of 220 volts. Okay, then we need to vary the loads now. Vary the loads. The loads are varied. So as the load is varied, your current will be varied. So as the current increases, your terminal voltage decreases. Your terminal voltage gets decreased. Let us assume that this is going to be 210. Okay, and or you may observe that this is going to be 230. Okay, and again increase the load, then this may be 205 and 235. Just I'm giving the two cases. This voltage, this voltmeter may show you this type of reading or this type of reading. Okay, so this is a 3, this is going to be 200 and this is 240. Okay, and 4, if you increase the load current to 4, so this is going to be 190, then it starts decreasing again, this may be 230. Okay, and then the field current is 5, your voltage may be 180. Okay, this is a for 5, this is going to be 180, then this is going to be 220. Okay, is it clear what I'm showing you? అర్థమవుతుంది అందరికీ? ఏదైనా డౌట్ ఉందా? Just I'm showing you two different readings. Okay, so this is the 220 initially, the voltage maybe gets decreased or the voltage maybe gets increased. Just you see here 220 నుంచి 230 కి వచ్చింది, 235, 240, then it is decreased and reaching the 220 volts. Okay, so you may see the three different cases. Voltage, the terminal voltage may be, the terminal voltage VT may be increased with the increase of load current. This is the case 1. And for the second case, the voltage may be increased and then reaching the rated voltage, then decreases, with the IL. Okay, with the IL increase. Then the third case is terminal voltage is always goes on decreasing with the increase in the load current. Okay, what is the first case? Anyone? What is the first case? Your terminal voltage is goes on increasing with the increase in the load current. And the second case is the terminal voltage increases, then decreases, reaches the rated value, then again decreases. This is the second case. And the third case is terminal voltage is always decreases. Okay, so here I will consider this the external characteristics. The first case is with the increase in IL, it results in the increase in the terminal voltage. And the second one, with the increase in the load current, the terminal voltage increases, then decreases. And the third case, IL increases, then your terminal voltage goes on decreasing. And this is a case only for the cumulatively compounded machines, because phi t is equal to phi sh plus phi se. This is for cumulatively compound generators. So this you can observe these three cases, because the flux is high, the flux is increased, so your terminal voltage is increased. So this type of generators is known as over compound generators. Okay, always the terminal voltage increases, so therefore this type of generators are called as over compounded generators. And in the second case, as the terminal voltage increases, then decreases, and it will be equal to, the terminal voltage will be equal to the no load voltage EA at full load condition, then after that your terminal voltage goes on decreasing. So this is called as a flat compound generators. And then The third case is IL is increases, your terminal voltage is decreases. This is known as under compound generators. This is for under compound generators. Okay, so the next one is the differentially compound generators. As for the differentially compound generators, phi t is equal to phi sh minus phi se, and therefore always the net flux is goes on decreasing. Your terminal voltage will be decreases always. Okay, Vt is always decreases. So with the help of this, now these are the characteristics you can observe. I will take up another slide here so that you can easily understand. So can you see this? Okay. So can you see this now? So in the first case here, first one you can observe that. So this one, this is as the load current is increasing, your terminal voltage is goes on increasing. Always it is increasing, and therefore this is called as a over compound generators. Over compound generators. And the second case, yeah, this one is the second one. The voltage is increased, then it is goes on decreasing and reaching the terminal voltage at the full load condition. At the full load condition, your terminal voltage is equal to no load voltage of EA, and therefore this is known as the level compound generators. And the next third one is just you can observe here. Third one is this one. So this is for under compound. So always the terminal voltage goes on decreasing. So this is always goes on decreasing, and therefore this is for the under compound generators. Okay, and if you want to compare it with the self-excited and shunt generators, so this is what. So as compared to the shunt and separately excited generators, the reduction in the terminal voltage is very less for the compound generators, and the reduction in the terminal voltage is for the shunt excited generators is more because your armature current consisting of load current plus field current, but your separately excited generators consisting of Ia is equal to IL only, and therefore the net current is less, so the drop in armature resistance will be less. Okay, so always all these are with respect to Ia, and therefore the drop in this armature resistances are very less. And you can observe this. This is for the differentially compound generators. So these are having a very huge voltage drop because of the net flux will be very less. Okay. So this is about the external characteristics of compound generators. Is it clear? Anyone is having any doubt?
Yes, sir.
Clear? Then next, take a screenshot of this. Just you go through the applications of DC generators. All of you take a screenshot. The separately excited generators are used in laboratories for testing, and they are having a wide range of output voltage, and they are used in electroplating and electro refining of materials. And these are also used for the supply source for the DC motors. And the shunt generators, they are used for lighting purpose, used to charge the batteries, and they will provide excitation to the alternators. Alternators are nothing but AC generators. Okay, and then next the applications of series generators. So these series generators are used in case of DC locomotives for regenerative braking, and they are also used as a booster in distribution networks. So in distribution networks, the voltage goes on reducing. So we need to boost up the voltage. So because of its characteristics, as the load is increasing, the voltage is increasing. and therefore they are used as a boosters. Okay, and then the compound generators. So over compound generators are used for lighting and also for heavy power supply purposes. And the flat compound generators are used for offices, hotels, homes, schools, etc. And differentially compound generators are very rare in use and mainly used for the arc welding. So this is a special application in the arc welding. Arc అయినప్పుడు మనకి short circuit అవుతుంది. So the voltage will be very less. So for that purpose, we use this differentially compounded generators. Okay, so these are the applications of the DC generators. So now I will close this first topic at this point. So tomorrow we will discuss about the DC motor operation, and also we'll see the back EMF and the torque generation in DC motors. Okay.
Okay, sir.